The topic of solutions, I don't know why I labeled it Chapter 10. I shouldn't have, perhaps, because every text is different, and maybe your text is different, and my bad. But the topic is solutions, or making solutions, dissolving stuff in water. I just wanted to go over a few models, structures, and vocabularies to make sure we're all on the same page here. So salt dissolves in water, sugar dissolves in water, many salts, many solids do dissolve in water. Water is called the universal solvent. It dissolves so many things. Um, yeah, water is called the solvent, and what gets dissolved is probably called the solute. Although the solvent doesn't have to be water. It could be something liquidy. It could even be something gaseous. I could say one gas dissolves another gas. Sometimes we say that the part that's in the larger component is the solvent and the smaller components is solute. But even that definition gets bent because, say, for example, alcohol and sugar dissolve perfectly well in each other. What if I'm sorry, alcohol and water, what if I had 50 milliliters of alcohol and 50 milliliters of water? They would dissolve in each other perfectly well, and I wouldn't know which one's a solute and which one's a solvent. But in any case, these are the words that we throw around a lot, just because they're sort of useful in most cases. In order for something to dissolve, like these purple ions, or maybe they could be molecules, this purple crystalline structure here, if this is the water and this is the solvent and this is the solute, the forces of attraction between the solvent and solute must be greater than the forces of attraction between the solvent and the solute and the solute. So if these forces are weaker and these forces are stronger, we will see dissolving. For example, with just table salt, I have the negative end of the water molecule attracted to the positive sodium, and that's evidently stronger than the force of attraction between the sodium ion and the chloride ion. And similarly, the positive side of the water is attracted to the negative chloride ion more strongly than this, and so that's why we think that ions, salts, and even sometimes molecules would have to have something else special about them, with not particularly the static electric charge of plus minus, but namely they should be lopsided like a sugar molecule, be polar. So in this cool model, we still see some blue here. What's in this blue? The answer is more water. What's in between the water molecules? Probably not too much. But in any case, just looking at some of the molecules in question, the molecules of water surround in 3 dimensions the positive sodium ion with the oxygen side pointing to it, and similarly the positive side of the water is attracted to the negative chloride in 3 dimensions. So it's kind of like a cutaway version. We aren't seeing the ones in front or the ones in back, the water molecules in front or back, but they're there surrounding the chloride ion and everywhere in between. But I guess in between here and here, if there's no other ions, then the water molecules still have hydrogen bonding / dipole forces, but not in the vein of spirit of dissolving. A couple other images I just clipped a little bit blurry off the internet. Something to think about. That when a salt dissolves in water, or even when something that's not a salt like sugar, or what's another molecule? Just an alcohol molecule dissolves in water, they are surrounded by or attracted by the water particles. They're solvated into solution. Yeah. Question: if water is able to dissolve so many things because of the electrostatic forces of attraction, or we could say polar forces between the dipole of water and the dipoles, semi-little dipoles of sugar, why can't it dissolve all salts? What allows water to dissolve salt but not silver chloride, NaCl but not AgCl? Well, as I mentioned a minute ago, the forces of attraction between the water and the ions in the salt must be greater than the attraction between the ions themselves. It's not exactly lattice energy, because lattice energy is technically breaking the ions up into gas phase ions, infinitely far apart. Here we're bringing them into a solution with just water. But, you could use the idea of lattice energy to say some salts have a great lattice energy, meaning the ions are sticking together very strongly, and some salts have a lower lattice energy, allowing, saying, the forces to break up those ions in the lattice of the crystal less, allowing water to break it apart. Okay, I said that. All right, cool. So, oh yeah, what's the difference then between salt and sugar? Just to make sure, the salt ions, be it positive, negative of any kind, are positive and negative, and they make good electrolytes in solution. So these little critters here help conduct electricity. But if I were to dissolve sugar molecules, it's hard to see that there's a sugar molecule in here. It's a hydrocarbon with some OHs around it that, yeah, this doesn't say sugar, it says molecular compound. So there's some molecule in here that's able to be surrounded by H2O. It probably means there's some OH groups on the molecule, and the OH groups of the molecule hydrogen bond and are attracted to the water molecules. That's what allows water to dissolve sugars and alcohols. Oh, here's the sugar. Speak of sugar. Speaking of sweetness. Sugar. Oh, so the OH groups, and as well as the lone pairs on the oxygen, I suppose. But especially these OH is all the way around the sugar molecule. And I drew the positive side of the water attracted to the negative lone pairs on the OH group. And I suppose even this hydrogen could possibly be attracted to a negative oxygen somewhere else. That's what allows sugar to dissolve so well in water. Excuse me. Can you see why these molecules are easily dissolved in water? And alcohol, OH, so that's similar to water, and this is similar to water. And this, these lone pairs also hydrogen bond with hydrogens of waters, and this is pretty lopsided as well. Soluble salts dissociate or break up into ions in aqueous phase, functioning as electrolytes. They conduct electricity really well. And molecules, if they dissolve, don't break up into ions. That is absolutely key. Concentration, qualitative versus or quantitative descriptions. We will go into this in a different video. What? Yeah, that should actually say qualitative. Who typed this slide up? Anyway, not me. Qualitative descriptions, concentration, some kind of description of how much solutes and how much solvent. If I say it's dilute, I mean it's diluted. I mean it's kind of watered down, assuming water is the solvent, although that's not always true. Other things can dissolve, do the dissolving as well, but dilute means not much solute in a lot of solvent. Concentrated means just the opposite, a lot of solute and a little bit of solvent, or relatively speaking, a lot of solute. So HCl is an acid that's in your tummy, but it's also comes sold in a bottle purified. Of course, in your tummy there's all kinds of enzymes and organics thrown in there as well with the hydrochloric acid. But anyway, the concentration of the acid is about 1/10 of a mole of acid in a liter of stomach juice, as compared to 12 moles of HCl in 1 liter in concentrated hydrochloric. It's so concentrated that you can actually see it, the gas, HCl gas, interacting with water vapor in the air, and you see it steaming up off of it looks like it's smoking. It's called fuming hydrochloric acid. 12 molar is a lot more concentrated than 0.1 molar. Most folks consider 0.1 molar diluted, unless you're talking organic biochemistry. In some cases that might be concentrated as compared to certain concentrations of certain ions or species and molecules. There's no dividing line between dilute and concentrated. It's sort of like, well, I don't know what's what, but like I said, most folks consider 0.1 molar fairly dilute. 1 molar is fairly concentrated. Alright, see you in class. Thanks for watching, guys.